Hi, I'm Carleton Coffrin, and it's my pleasure to be giving you this JuliaCon talk about benchmarking nonlinear optimization with AC optimal power flow. I would also like to acknowledge the contributions of Oscar Dawson, who has been a great help in preparing a lot of the results I'll show in this talk. Let me begin with a bit about me. So I am a computer scientist, and I'm trained in designing optimization algorithms. I've been a staff scientist at Los Alamos since 2016, and also got my PhD in 2012. In my day job at Los Alamos, I'm designing optimization algorithms for critical infrastructure networks. These often take the form of mixed integer nonlinear optimization problems, so they contain both discrete and continuous variables. And as part of that work, I develop production optimization software, which is used to advise various stakeholders in the US government. And I try to open source as many of the tools that I develop as possible. I've been using Julia and JUMP since 2016, and I'm a core developer of the infrastructure models ecosystem, which, if you're interested in learning more about that, I did a JuliaCon talk in 2021 about it, so go check that out. In this work, I'm interested in nonlinear optimization methods, and this is not a particularly new topic. There are many commercial tools and open source tools out there. And in general, I'm interested in the fastest, most scalable solutions that are out there. So I'm showing images of some of the tools that are out there. The Pyomo, Gravity, and JUMP are open source, and the other ones are commercial tools. Let me mention briefly why the team I work in has been using JUMP since 2016 for our nonlinear optimization needs. In the beginning, back in 2016, this was the only free and open source tool that we found that served our use case, which is to be very scalable and be able to run in parallel on large HPC clusters. So licensing is problematic if you have that type of use case. We also observed it had a unique combination of features, and I think this is true even today, that JUMP is the only modeling layer where you can do both conic optimization and nonlinear optimization. And we also found that Julia's just-in-time compiling system provided an ideal setting for tooling around JUMP, because there's a lot of data processing when you're doing optimization. So high performance of Julia was a big help as well. So why should you care about this talk and nonlinear optimization in general? Well, it was observed after last JuliaCon very well by Francois Picot that there's a growing interest in nonlinear optimization in the Julia community, and Francois has set up a Julia NLP developers call once a month for that community to be built and coordinate. So I highly encourage you to join that particular call. But what I'll show you in this talk is for the kind of optimization problems that I run into in my day job, JUMP is a really high performance and fantastic tool. I'll show you results that JUMP can be up to 415 times faster than the next best option I could find in Julia. And I'll make an argument that maybe it's even 50,000 times faster than that next best option. So work is ongoing to improve nonlinear optimization in JUMP, but I think already it's an extremely high value asset for the Julia ecosystem, and I would encourage everyone to give it a try and see what it can do for them. In my opinion, it's effectively a commercial quality software tool, but you can have it totally for free. So here's an overview of what I'm going to cover in this talk. So I'm going to begin with surveying what Julia frameworks exist for solving nonlinear optimization problems. I'm going to discuss how we can to make an approach to benchmarking those different frameworks, and then report on what we found by doing that benchmark. I'll conclude with a little bit of my perspective on the outlook for nonlinear optimization in the Julia ecosystem. So what is nonlinear optimization? In my particular experience, I'm interested in solving nonlinear problems that have the form that is pictured on the right here. So you're going to have X, a vector of decision variables, which is say of length n, and you're going to try to minimize the assignment of those variables subject to some function f, where there might also be constraints like g, which set strict equality on those variables, or inequality constraints h, on those variables. So altogether, you have a constrained, continuous optimization problem. But what makes it really interesting is that these functions f, g, and h might be non-convex and nonlinear functions, which can lead to very challenging behaviors in terms of their structure and how to minimize this vector x. In particular, in the work that I do, we often have polynomial functions of these variables x, like x squared times y to the cubed, or transcendental functions like the sine function. The problems we face are very large scale, so n is a large number, but they're also very sparse, so very few variables participate in each one of these constraints or the objective function. And I think it's important to note that when you're working in an environment like a national lab, you generally don't have time to develop hard-coded derivatives for these functions, f, g, and h. And so this automatic differentiation systems, which compute for you the derivatives of f, g, and h sparsely, is really, really valuable and essential so that we can do rapid development on these different optimization models and not have to worry about keeping a bunch of derivative functions in sync. So with those requirements in mind, I conducted a survey of nonlinear optimization modeling tools in Julia, and there's a great post on Discord, which you can check out to see what that whole discovery was and how it started and some discussion around it. Ultimately, I identified these few packages which could potentially solve nonlinear optimization problems, but not all of them had the features that I needed for my particular use case, non-convex, nonlinear. But after you down select to the features that I need, you're left with 5 different optimization modeling layers, which could potentially solve this particular class of problems. So this is NLP models, jump, non-convex, optim, and optimization, which was previously called galactic optim, if you're familiar with that name. So these are the 5 I'm going to focus on for the rest of the talk. Now, let's talk briefly about how we can do nonlinear optimization benchmarking. Ideally, I would be able to share with you all the types of optimization problems that I solve in my day job, but there are some sensitivities with sharing particular implementation details, the specific functions that we're solving, and also the data which builds these models. And this is true for many application areas in national labs. So the HPC community has developed this idea of proxy applications, which are not exactly the problems we solve, but are a good tool for measuring the type of features we need to solve the problems we want to solve. So what I am proposing in this work is that AC optimal power flow can be a useful and helpful proxy app for the kinds of nonlinear optimization problems that I face at LANL, and we can use it to evaluate these different nonlinear optimization modeling layers. So I believe that this problem is kind of a minimal viable problem for demonstrating practicality. If you can't solve this, you have little hope of solving all the more challenging problems that we face in my line of work. A nice advantage of studying this problem is that there's a standard benchmark library, pglibopf, that we can use for getting the data sets you need. And this particular benchmark library yields optimization problems with as few as 24 variables, but as many as 200,000. So you can really check a huge range of scalability. And just for perspective, the industry in energy systems is expecting solutions to these problems in seconds to minutes. So they present a pretty big challenge for optimization tools because there are so many variables and you want to solve it so fast. Just briefly, what is AC optimal power flow? I would call it the most canonical power network optimization problem you could consider. You're given a network, which is illustrated on the right, which is organized in nodes and edges. And your interest is to find the cheapest way to generate power so that you can serve the loads in the network under some particular operating requirements. So in this picture, the down arrows are the loads and the circles are the generators, and over the lines, there'll be flow limits. For example, we call this node a network bus. And it's important to know that it's called a bus because this is usually used to measure the size of the problems you want to solve. And in particular, I would say that problems with less than 500 buses are generally considered like toy problems for teaching. Between 500 and 5,000 buses, we have kind of academic R&D scale problems. And then industry is really interested in solving problems with like 5,000 to 50,000 buses because that's how big the geographic footprint of real power networks is. So what form does this type of optimization problem take? It's a complex, nonlinear, continuous nonlinear, non-convex optimization problem. This is the complete form that you would have. And if you look at this particular constraint, it ends up being a continuous convex constraint, like a circle. And if you look at this constraint and break it down, you're going to have some very interesting non-convex polynomial function with things like a squared in it, a times b times cosine of a difference, and all strictly equal to another variable, so that makes it non-convex. So inspired by this Rosetta Code tool for learning how to program in different programming languages, I propose the idea of a Rosetta Stone for optimal power flow, where we re-implement this ACOPF problem in all the different modeling layers in Julia to see how what they look like, and then ultimately how they perform. So I've built this repository called Rosetta OPF, which includes OPF problems in all of the Julia nonlinear modeling tools. It started with the 5 that I presented earlier, but I'm very much welcome new ones if new modeling layers show up. I would also note that I'm not an expert in all of these modeling frameworks. I learned them only to do this project. And so PRs with new models or improvements to the current ones are definitely welcome. I suspect there's low-hanging fruit to improve the implementations that I have. Okay, so now we have optimal power flow problem. We have the nonlinear optimization frameworks. Let's talk about benchmarking them with that optimal power flow problem. In particular, it's maybe not super clear how nonlinear optimization algorithms work and how you might benchmark them. So to understand that, we need to talk a little bit about how they work. So as a user of nonlinear optimization, you're used to seeing this modeling layer, which I'm calling the NLP modeling layer, where you write your system of equations and your variables and constraints. This modeling layer then generates Jacobian and Hessian oracles for evaluating your particular problem and hands those oracles off to the NLP algorithm. So the algorithm doesn't usually know the details of your model, it just knows there's some sparse matrices which represent the Jacobian and Hessian. And then the NLP algorithm goes between queries to the Jacobian and Hessian oracles and linear system solvers until it can converge to a common point. And ultimately, it will, when it converges, it returns the solution back to the NLP modeling layer, and that's where you get your solution back out again. So there's all these different moving parts. In this particular experiment, I'm going to hold the algorithm fixed to IPOPT 3.14, and a linear solver mumps 5.4, and then these are what comes standard with Julia if you install these different tools. And what this means is, because those are held constant, what we'll be measuring is really what's it like to implement the model in this modeling layer, and then how good is it at building some Jacobian and Hessian oracles. Now, before I show you any results, I want to give a couple of big warnings about what you're going to see. I mentioned already, I'm not an expert in these modeling layers, so there could be improvements there. I'll note that the development of the packages optimization and non-convex is moving very quickly. So I would encourage you to check the latest versions if you're watching this talk, because there might be dramatic improvements since I implemented these and collected these results. I show you the versions of the packages I use on the right here. For example, when I started doing this work, these two methods could not even solve basic ACOPF problems, and now they're solving ones with up to, say, 100 buses in them. I'm going to show you runtime results, and I should note that the Julia setup times have been removed. So it does not include just-in-time compiling. You may see a little bit longer runtimes if you test on your local computer, but I think it's best to remove these because in my experience in a production setting, there's always a way of doing pre-compilation so that you can avoid them in practice. There is a nice discussion on Discourse called AC Optimal Power Flow and Various Nonlinear Optimization Frameworks, where I'll show the raw data that I'm going to present to you here. And it's a great place to continue the discussion if you have some interesting remarks to make about this. Okay, so I'm going to begin with this particular plot where we have the size of the OPF problem on the x-axis, and we're looking at the number of variables in the optimization problem there. And then we're going to have the runtime to converge to a particular solution in seconds on the y-axis. And these are both in log scale, so this is a log-log plot. I've also indicated 2 points with dashed lines, and the first one represents a 500 bus network. So this is the point at which you start to go to interesting problems. The next one is the 5,000 bus network, and this is where you go to industry relevant problems. And this represents about 40,000 variables. So if these are what I called before the toy problems, these are useful for teaching or doing very detailed analysis of a particular structure of the problem, but it's hard to publish papers on this problem scale. Then we have this scale, which is pretty common for writing academic works, and then we have this scale, which is the real world size problems. So here is the initial raw results for all 5 of these frameworks. And we have JUMP in blue, we have NLP models in orange, non-convex in green, and optimization in red. You will notice that you don't see the Optim package in here. And that is because despite my best efforts, I was not able to get that working and converging on any of these instances. Optim was the only package where I couldn't use IPOct as the solution algorithm, and that seems to have presented some difficulties for converging to such a complex optimization task. But again, PR is welcome to fix the Optim implementation if you're an expert in Optim. So the first note I would make about this is that all of the modeling layers except for JUMP are sitting in this particular box that I've highlighted here, which is in this toy model region. So there were a number of challenges, runtime being one of the biggest ones, that prevented me from solving larger problems with these different modeling layers. In particular, I mentioned at the beginning of the talk that I would show you JUMP could be potentially 415 times faster than the next best option. I'm pulling that number from this particular data point, where if we look at the largest problem we could solve with the various competitors and the fastest solver, that was optimization. And it's compared to JUMP is about 415 times slower for this particular problem size, which I mentioned before is about maybe 100 buses, several hundred decision variables. But this leads to a natural question, like if we had infinite compute time, what would all of these different methods do? And to do that, I proposed to fit a model of the scalability of these different methods. And you can see that fit right here. And these log-log plots can be very deceiving because these look like straight lines, but they're actually quite dramatic differences in performance. So at this point right here, this is the largest instance that we checked as part of that pglib benchmark library, and it takes 350 seconds to solve with JUMP. The next best fit model would take 209 days if it followed this trend line that I've plotted here. And then this one would take 20 years to solve, and this one would take 1,400 years approximately to solve. So quite a big difference. And at the beginning of the talk, I mentioned a potential 50,000x speedup. That comes from this analysis here, where if you project it out to the largest problem sizes that we would like to benchmark, this is where you would be sitting, and there's a very dramatic runtime difference here. But this is just speculative because it's a projection and not real data. In any case, I would believe that anyone looking at this would think this is absurd. How could there be such a dramatic difference in all these different optimization layers? And I'll just go into my best understanding of what's going on. So I'm interested in solving nonlinear optimization problems of the form to the right here. So they have a simple arithmetic form through a series of functions that may be polynomials, including some transcendental functions, like standard C floating point type of expressions. Both JUMP and NLP models focus on solving that particular type of problem, but NLP models doesn't take advantage of sparsity as far as I can tell. And so the major hit you're seeing there is how much can you scale if you're not taking advantage of sparsity. And as I mentioned before, optimal power flow is an extremely sparse problem, so you really need to take advantage of it to scale. For the other two major options, optimization and non-convex, I would argue it's a bit of an apples to oranges comparison here. The reason is that these packages are designed to support arbitrary Julia functions, so they're much more general than JUMP and NLP models. They go way beyond the model I'm showing on the right here, and I believe what we're seeing is the overheads of processing this arbitrary Julia code into derivative oracles is non-trivial. So what I think is happening is that JUMP is getting a huge performance gain by dramatically reducing the scope and only looking at NLP and handling sparsity really well. So it's a delicate interplay of the optimization modeling layer and the auto-differentiation system, which allows you to scale to such large problems. So JUMP is great. But I hope I've convinced you of that so far. But the important question, is it really the greatest in the world? There's many other tools we could potentially use out there to solve these types of problems. So to answer that question, I looked at the state of the art for solving AC optimal power flow. There's been a very recent paper about a tool called OPOMO, which is built in this gravity modeling layer in C++. And in that paper and in this website, you'll see this particular plot, which shows how much slower different tools are than OPOMO. And it says power models up there, but you can just think of this as JUMP, because that's all power models does, is build JUMP models. And if you look at this, especially in the large instance limit, this JUMP-based model is about 3x slower than OPOMO. So it seems like we have about 3x to be gained compared to state of the art. So I repeated this same experiment using the same plots, but with this OPOMO solver. And now these are no longer in a log scale. So we have variables and runtime seconds in a linear scale. And I'm going to focus my attention on the largest problem we can solve, which is over here. And by looking at the difference between the purple dot, which is OPOMO, and the blue dot, JUMP, you can see that there's about a 3x runtime gain, which exactly matches what was reported in that previous slide. So we've reproduced those results. And the question is, can we make JUMP faster? Interestingly, OPOMO and JUMP use the same NLP algorithm in the same linear solver. So the potential gains all come down to how can you implement this particular Jacobian Hessian oracle in the modeling layer. And we have an ongoing effort in JUMP to support different types of auto-differentiation backends. We have this NL file interface. There's a very new symbolic AD system and a MAD-diff system, which have been developed by different folks. If you want to hear more about that, check out Oscar's talk. But what you can see here is when you benchmark with those different auto-differentiation systems, you end up improving upon JUMP's performance quite a bit. And in particular, for example, using the symbolic AD system that Oscar built, we were able to close this gap with OPOMO down to about 1.5x. So a pretty big improvement over JUMP's default system. So I'll just wrap up with my outlook for nonlinear optimization in Julia. JUMP has great support for large-scale nonlinear optimization problems. It's with very close to state-of-the-art, maybe 3x slower. So that's a great value for the community. If you're interested in solving mathematical programs and not black box Julia code, JUMP can potentially give you a really big runtime performance boost, like I showed in this talk, of 400x. And automatic differentiation systems do have a really big impact on performance. So I showed a 3x speedup on optimal power flow here. So new versions of JUMP are going to be better for allowing users to choose differentiation libraries that work for their particular problem structures. Thank you very much, and I'm looking forward to answering any questions that you may have.